Subsequences are important tools when we deal with sequences. So let's see what they are. Given a sequence of numbers, we call a subsequence a selection of elements from the principal sequence AN that respects the positional order. This is not yet a mathematical definition, so let's practice this idea on examples in such a way that we can understand what we want really. So imagine that we have a sequence AN and consider this sequence made of some of the elements of this sequence. The sequence is A0, A2, A4, A6, A8, you may imagine A10, A12, and so on. So what we are selecting from this list are elements at positions 0, 2, 4, 6, 8, and so on. So these are even positions. So we may imagine that this is the sequence whose general term is A at positions 2k. A similar example is this one. Here we have elements selected at positions 1, 3, 5, 7, 9, 11, and so on. So these are odd positions, and so the general term of this could be A position 2k plus 1, where k is a natural number, because 2k plus 1, when k is natural, represents all odd numbers. In this third example, we have a selection from AN taking elements at positions 0, 1, 4, 9, 16, and so on. You may imagine that these are squares of naturals. So in general, I'm selecting A at position k square, where again k is a natural number. In this last example, we have a selection from AN of elements at positions 1, 2, 4, 8, 16, 32, 64. So these are powers of 2. We can say that we are selecting A position 2 to power k. Before we formalize the definition, let's see a couple of examples of sequences taken from AN which are not considered subsequences. Here we have the sequence A1, A0, A3, A2, A5, A4, and so on. If you look at positions, here we are selecting position 1, then position 0, position 3, then position 2, and so on. So what happens here is that we do not respect the positional order, because position 1 comes after position 0, not before, as well as position 3 comes after position 2, not before, and so on. So this is the problem with this sequence. So it is a sequence, but we do not consider a subsequence. And also in this second case, we have something wrong. If you look, we have positions, the selected positions are 0, 0, 1, 1, 2, 3, 4, 4, 4. So it seems that we respect the positional order, but you see the second element is a repetition of the first, so the second position does not come after 0, but is just equal to 0. So it's the same position. We don't want this case, so we don't want to introduce repetitions. So we must respect in a strict sense positional order. So now we are ready to write down a definition. So to define a subsequence, we need to specify which elements we choose from AN. So which positions are we taking from the principal list AN? So the key ingredient is a sequence of positions that we can represent as a sequence of natural numbers. And since we want to respect the positional order, this condition can be written on the AN in this way. The first position selected is N0. It must be strictly less than the second selected position, which is N1. This at the same time says that you cannot take 2 times the same position because of the strict sign. And the third position must be greater than the second, the fourth greater than the third, and so on. So it is a strictly increasing sequence of natural numbers. These are the positions. So if we now take elements at those positions, so A position nk, this is the list AN0, AN1, AN2, and so on, we get a new sequence, and we call this a subsequence of AN. The first important property of a subsequence with respect to a sequence is this one. It is relatively simple to be proved, but not so easy. So there is a little trick that you could try to prove this as a nice exercise. But don't be scared if you do not arrive to prove completely this. However, it says, if you have a sequence AN that has a limit, finite or infinite, doesn't matter, then every subsequence ANK will have the same limit. What is important of this property is a logical consequence of this. That is, suppose that now you have two subsequences of AN, let's say A and K, A and K, that have two different limits, L1 and L2. So what happens to the sequence AN? Well, it happens that it cannot have a limit, because if AN has a limit, all subsequences must have necessarily the same limit. And here you have two, you are supposing that there are two sequences for which you have two different limits. So the interesting part of this story is that you have a test to check that a limit does not exist. Let's see on a practical example. Take the sequence -1 to the power n, which is a very frequent sequence we find in mathematics because it generates an alternating sign. Well, we can accept that -1 to 0 is 1. If you don't like this, start from n equal 1. So from n equal 1, -1 to 1 is -1. For n equal 2, -1 squared is 1. And then -1 cubed is -1, and so on. So here you may notice that if we select elements at positions 0, 2, 4, 6, these are 1, 1, 1, 1. So the subsequence made of elements at position an even number is constantly equal to 1, so it goes to 1. If you do now the selection of elements at positions 1, 3, 5, 7, so odd positions, you get -1 to an odd number. This is constantly equal to -1, and therefore will go to -1. So here you have the two subsequences that have two different limits. Therefore, the full sequence cannot have a limit. So, in general, we come to see that a sequence, if you take a sequence at random, in general, you cannot say that there is a limit. For example, the sequence -1 to n has not a limit. There is, however, a remarkable and deep property that can be proved. The proof is very difficult. I do not invite you to try to prove, but if you want to try, it's an extremely good challenge that says the following. Take a sequence, arbitrary, a sequence AN in the real line. Then, there exists always at least a subsequence ANK of your sequence that will converge to something, finite or infinite. Now, what are the next steps? Well, first, I would suggest you to try to practice the non-existence of limit test, that finds two subsequences of a given sequence with two different limits on a few particular cases. So here you have to exhibit explicitly the two subsequences of this, of this, of this. For each of these, there will be a different subsequence with two different limits, and conclude that there is no limit for the sequence. If you want to do a step forward in comprehension, to improve your comprehension, you should now try to move on a more abstract level. For example, trying to prove a general property that is not referred to any particular sequence. Imagine that you have a sequence AN, generic, such that the subsequence of elements in even position goes to L, and the subsequence of elements at odd positions goes to L as well, the same L. Then the conclusion is, it doesn't matter what is L. The conclusion is AN goes to L. Now, you should try to prove this by using definitions And this is something that you can do. Have fun.